actually, this is not a coincidence that the slope of this regression line is giving us the beta. I've motivated the beta up here. We could have used the covariance itself, right? But why don't we do that? Well, first of all, if we divide by the market variance, we can standardize the measure. That means that we have the centered value at 1, right? And it gives us a nicer way to interpret this. And the second thing is that this number here is, in statistics, the coefficient in the regression, right? So people were looking at this, okay, we can use regressions if we define the beta that way, right? It's not a coincidence that it's the same. Furthermore, the regression gives us the opportunity to extend the model, right? So here we have now tried to forecast the BioNTech return using the market only, but we could use more variables if we have other factors that impact the return. And this is something that I'll at least show you. So there's a model by Farmer and French. Eugene Farmer is a Nobel Prize laureate. And he extended the model by 2 additional factors. He said firm size should be incorporated and the book to market value ratio, book value to market value should be incorporated. And basically how you do that is by having a regression with multiple regressors, with multiple variables. It's a kind of an empirical model, it's not a theoretical model, but it's kind of one that's very often used to estimate returns better than just with the market. Right, so it's a nice approach that we can extend. Right, so the formula of the sample regression line looks like this. So the BioNTech return is equal to the alpha plus beta times the DAX return. That's the red line. And here are the estimated values, 16.16% for the alpha and minus 1.26 for the beta. So here's our beta. BioNTech, so it's negative. So again, this here was the part of return that's related to the market. And then we have the part of the return which is unrelated to the market. So at least in research, this would be the approach that's most often used to estimate the betas because you can already get the alphas from the same kind of computation. And in Excel, there are formulas for this. They're called intercept and slope, right? That they're inbuilt functions that you can easily use to get those 2 numbers. But theoretically, all the approaches that we have should yield you the same result. But even if you kind of have troubles with statistics, I think the graphical representation should be intuitive enough. So we don't run regressions in this class. I'll show you to do that, but it's not kind of relevant for the exam if you're worried about this. So I'll leave that to any statistics course or data analysis course that you have. Are there questions regarding kind of this way, the 2 ways of estimating the betas? Well, we can come back to this also when we do the data work and before or after the break. Because what I found quite interesting here is that I've used monthly returns here, and I've done that for a purpose. I mean, I was looking for an asset with negative beta, and then I was trying this out with daily returns. It was not working. So the beta with daily returns is positive, unfortunately. I was really, really weird, but so either I made a mistake somewhere in my computations, or it's just a weird data artifact that if you use monthly returns, or it works, and on daily returns, maybe there's so many other things that happen that kind of distort the analysis. Generally speaking, we'll face kind of a trade-off in these kind of things when we kind of look at what's the correct data to use for this, right? From a statistical point of view, and also for regressions, you want to use as much data as you want, so you want to go back as long as you can. Well, here we are limited to data availability to November 2019. Yeah, but from an economic point of view, we want to use data that's representative for the thing that we're analyzing today. So if there was a merger sometime, we shouldn't use data from before the merger because that was a different company. So if you use estimate betas and volatilities from daily data, so typical approach is to use 1 year of data, so 252 data points. If you use monthly data like here, that's probably not enough for a good statistical analysis. So if you use monthly data, probably you would use 5 years. You would have 5 years times 12 months means 60 data points. That's kind of the thing that's common in practice. Right? So these are the two versions that I see most often. Right? Either daily data and the 252 days, or monthly data and use 5 years. Okay, so if there are no further questions, then let's move ahead to the next chapter. We're actually continuing with the example for a little bit. So this chapter is basically divided in 2 parts. So we start first with measuring the risk of portfolios and computing the same risk measures as before, or the same returns and volatility and beta measures. So theoretically, you could just do it the very same way as we did it before. You can treat a portfolio like a collection of many different assets. You can treat that as a single security and then use all the formulas from last week. So in some instances, that's actually doesn't make a difference. However, if you, for example, know what the betas of all the securities in your portfolio are, remember the beta computation was quite tedious with the covariance, right? It took us a lot of time. There is a shortcut to do that for portfolios. So there are 2 measures, returns and betas, which we can compute much quicker for a portfolio. However, the volatility computation is a little bit more messy. Nevertheless, I want to introduce the full set of formulas, and actually for the rest of the chapter, I'm using one formula that we haven't developed yet. So a portfolio, or the minimum portfolio that we look at is going to be a portfolio of 2 securities. So what from a mathematical point of view becomes difficult here, that these are 2 random variables. So we have to think about, if you take the sum of the 2 random variables, like, how do the formulas change? Right, so in some instances we are faster, in some instances we are not. Right? So for problem sets and exams, you have to kind of work yourself and intuition kind of what the quickest way of doing this is. So sometimes you just spend lots of time on something that could have done much quicker. So definitely beta and returns are easier in this chapter, and volatility is probably easier in the way how we did it in the last chapter. But sometimes you're just limited by information that you have. If you don't have the full information, you just have to kind of go with one option for which you have the data. Again, all the formulas are on the formula sheet, so that shouldn't be a problem then for the exam. Now, that's the first part, and then the second part will be the actual portfolio theory. So the first part should actually be called portfolio risk measures, and then we go to the portfolio theory. And then we go to the portfolio theory. And this is a theory developed by a guy called Harry Markowitz. I think I have his name in the slides, so I don't have to write it down. And he was awarded for this by with the Nobel Prize in economics, together with the guys from the next chapter, Sharp, Mossen, and Lindner. So basically he asked the question, like, are there some rules that you should follow when you construct portfolios? So what is an optimal portfolio, basically? So we're starting in an optimization setting. So basically looking at the expected return, and the risk measure he uses is the volatility. And then he looks at maybe are there some portfolios which are good, which are optimal, and there are some portfolios maybe that we should not kind of consider, that we should rule out. So that's what portfolio theory is. Gives us some guidelines about portfolio construction, optimal portfolio construction. This theory then is the groundwork for the theory that we discuss next week, which is called the capital asset pricing model. So basically, it's an extension of this theory. Right? So all the results that we study in this chapter will be valid in the next theory as well, but they kind of continue this. They're adding more assumptions to it, and then they will develop the pricing relationship. So in this chapter here, we're still considering prices as given, like we observe the prices in the market, so we're not looking at what the correct price for something is. We're just given the prices and the risks that we see, what is the optimal portfolio that we construct. So there are several ways of deriving the portfolio theory. I start with a simple case with only 2 assets, and I will mostly graphically illustrate that. So there's, of course, if you do optimization, that should kind of ring a bell, right? So you can write down objective functions, compute the first derivative, and kind of solve that mathematically. But I think a graphical representation is fine for the context of this class. I will only use 2 assets. That's already complicated enough. But of course, you can extend this to 100 assets, right? So I will put in the formula for multiple kind of assets at some point. But this is more like for your information. If you are like in an internship or a job market or in a job context and you need to know what the formula is, most of the time in real life you have more than 2 assets. Right? So if you want to know the formula, it's in the slides. But we're working with a simple case of 2. Yeah. So there's actually one thing that before we move on to the formulas, that we kind of need to introduce. You can write down portfolios or portfolio values just very simply, and then use the values like you would treat a share. Like use it as a share price, and then from that derive returns. However, there's an alternative way of expression, and that is with the so-called portfolio weight. And I need to first introduce this concept to you, and we're using this portfolio weight quite extensively in this chapter. So let's walk through these formulas. So the first one shows you what the portfolio value is. Portfolio value is the sum of the values of the individual components of your portfolio. It might seem obvious, but there are people who spend time proving this, that the portfolio value is really just additive in its components, that there is kind of no... if you put two assets in a portfolio, you do not magically create additional value by that. Right? That's kind of the reasoning behind it. So if you have 100 shares of the first company, then the value of that would be 100 times the share price of that company. And then if you have 50 shares of another company, that will be then 50 times the share price of that company, then you just add up the numbers. Right? That's your portfolio value. Maybe for the very simple case of 2 assets, let me write this down. So N stands for the number of shares that you have, B is the price of that asset,